Welcome back to STEM Online Academy. My name is Jason, for those of you who don't know, and we are going to do another interesting problem-solving question today. Okay, so most students can find a tangent line, but this specific problem asks for something much harder. Don't be intimidated. Okay, which tangent line is best? I've made an actual image of what's going on in terms of the behavior. Okay. So as you can see, we have a curve y equals e to the x, right? That's the blue curve there. Okay. Right, so as you can see here is the pointer. Yeah. So this curve here is y equals e to the x. Okay. And the tangent line is that red line hitting exactly that point, right? So which tangent line is best? That's pretty much what the question that we're given is asked, right? Not the tangent line at 0, obviously, right? Not the tangent line at 1. The tangent line specifically to e to the x that makes the largest error, right? The tangent line to e to the x, sorry, that makes the largest error as small as possible on the whole interval from 0, right over here, to 1. This is exactly the kind of problem that makes sometimes even the strongest students going that will freeze up on calculus exams, right? Because it's not a standard tangent line problem. Okay, but we shouldn't panic on this. Okay, we're just going to use my system. Okay, so you've seen the graph here, right? Right. Now, what I've highlighted in red here is the result that we're supposed to get. We're supposed to find the value of a that minimizes the error function. Okay, so let's go back here. Okay, so our problem for a belonging to 0, 1, let capital L substitute a of x, that's the tangent line, to the function e to the x be represented by this. Okay, so this guy here is the equation of tangent line, and my error function is this guy over here. Okay, we want to find the value of a that minimizes the error function e of a. Don't be intimidated by it. All we are going to use, right, is we're going to use my systems technique. Okay, so let's do that. Okay, so let's go to the next page here. All right, so just give me a moment. All right, so I'm going to use my systems technique. Okay, so we're going to use the systems technique. Systems technique of mine. Right. So what is my systems technique? For those of you who are new, you don't know what it is, but I'm going to put it down, right? So it's visualize. Okay, so first you want to visualize. That means either geometrically, even algebraically too, doesn't matter. It's like you have a certain format, a certain framework that you're working with, okay? Uh, that you want to set up the problem with, okay? So visualize, then you want to model. You want to model, okay? Then you want to be able to execute. Okay, so you want to execute. And then verify. Okay, so you want to verify. That's what we're going to use to solve this problem. Right? So I'm gonna talk a bit about my own story a bit and why I started STEM Online Academy and this channel specifically. I used to struggle with mathematics when I was much younger, grade seven, part of 8. Yeah, I used to struggle with mathematics, and not because I could not learn it, but because I didn't have a system for hard, like those hard problems to deal with, right? For- with algorithmic problems, they're easy to solve. Anyone can do them. But for hard problems, you really, really have to think very smart and have a plan of attack in order to deal with them. Okay, you can't just have something that is formulaic and that sort of spits it out for you. No, it doesn't work with hard problems. Okay. Two teachers changed my life actually by showing me how to break difficult problems into a structure. Okay. Two teachers. Now, they didn't teach me this specific technique, but they told me that I have to develop a system that works. And I listened to them religiously on that. Okay. So the method that I have here, right, that I've formulated over the years, based off of all the courses that I've taken, that's how I came down to this being a very effective model. This method helped me master mathematics and physics, and graduate with a Bachelor of Science double honors in mathematics and physics with a 3.9 GPA. For those of you who don't know what a 3.9 is, GPA is, that's almost a perfect score at the end of my schooling. Okay, and from that, I was encouraged to build STEM Online because I knew I wanted to help um, people. I want to see if I can change their academic trajectory, for the better if they were struggling in in school, right? Maybe I can help them, have the same, maybe not the same success as me, but have a much better outcome and be able to go to university and be able to not just go to university but finish it uh, with amazing results. Okay. Now, I teach serious students how to solve hard calculus exam problems, right? With a repeatable solution, repeatable system. Yeah. Today, my mouth is like it's slipping for some reason. Repeatable system is the one I showed you right here. Okay. So when it comes to that, right, that repeatable system, and also independent learners. There's people who like to learn mathematics from advanced mathematics. This channel is also for them as well. Okay. So if you understand, right, the lesson, but you freeze when the exam problem looks unfamiliar, this video is for you. Okay. It's definitely for you. Right. So, especially if you want to crack exams with those hard exam questions, or as I said, you can be an independent learner and you want to be able to understand mathematics, advanced mathematics comprehensively. uh, Problems like these are good, right? They're going to train you to think out of the box. Okay. So we're given the function f of x, right? As I said, equals e to the x. Okay. At 7 point x equals a. Okay, so let's look at the problem. At x equals a, where a is between 0 and 1, right? So if you look up here, a is between 0 and 1 on the interval. Okay. So in other words, we want to find a tangent line that stays as close as possible to e to the x. That's what it's saying, even in the worst place. Okay. I like to call it the worst case error. So let's look at our diagram again, right? See what I mean? Right? We are looking where e to the x, where we can have our tangent line staying as close as possible to e to the x. Okay? I'm zooming in here. By the way, we want our result because when we're trying to find a value a that minimizes the error function. This is the value of a that we should be getting. Okay? I want to verify that. Right? So let's do that. Right? Let's do that. So first we visualize the graph, right? Right. So step one, you want to visualize. Let's go to the next page. Where is it? So I had you here somewhere. Damn it. Oh, right. So step one. Step one. You're going to visualize. Okay. That one. Let's get rid of this one here. Just 1 second. Yeah. So step one, I want you guys to visualize the graph, right? Well, here's very easy to visualize, and I've done the visualization for you, sort of. So step one, visualize. Okay. Let's visualize geometrically what is happening, right? With the y equals e to the x and the tangent line. Okay. So e to the x is going to be increasing and convex, right? Right? Y equals e to the x is increasing. Increasing. Has to be increasing. It's an increasing function. Increasing and convex. Okay. If you look here again, you can see that y equals e to the x, right? The blue curve. Okay. This blue curve is increasing. I think you can all agree with that. Okay. Now convex means that it's bending upwards. So you can see that curve is also bending upwards. Okay. This blue curve. That's why I said convex and increasing. And for a convex function, right, the tangent line is going to sit below the graph, right? So not only a convex function is bending upwards, its tangent line is always below here, right? As you can see, it is below the graph at the tangent line. So we're going to compare e to the x to its tangent line, right? Right. So we're going to compare e to the x to its tangent line. Okay. Now, so I'm going to write here. I'm going to compare it. Compare e to the x to its tangent line, and that's what this equation here is saying, right? E of a, right? E of a. This equation here that I've underlined in white. Okay. It's comparing the difference between the actual curve, right? The actual curve is e to the x, right? That we were looking at. I'm going to zoom in. E to the x minus the tangent line, L subscript a of x, okay? All right, so that's what we're doing. We're actually taking the actual curve. That's what it's saying here, right? So the error function, as I said, error of a, is actually just saying taking the actual, I'm taking the actual curve, and I am subtracting it from the tangent line. That's the error function, okay? If you have any questions, if something that is not making sense to you, please put it in the chat. Any questions, please put it in the chat. I always like to engage and have conversations. Okay, so you learn, and maybe even I can learn too. That's what makes a very good YouTube dialogue, when we can both communicate. Right? You learn interesting stuff from other people. It's very true, and that's what this channel is about. Don't think it's just about me rambling along. Question what I'm saying, right? Okay. So we have the error function here, right? So the error is always going to be 0 at the point of tangency. Point of tangency is this guy, okay? It's right here on this graph here, okay? Highlighted in red. That's the point of tangency, okay? So we know that the error is always 0 at the point of tangency because the tangent line is going to intersect the curve there, right? That tangent line intersected the curve. But away from that point, the error is going to grow, okay? I don't know if you noticed, but the error was growing on the graph. So the real question is now, right? Where is that largest error? That's what we're trying to figure out, right? Where is the largest error? So for this problem, the largest error is going to happen at 2 of the endpoints. Okay, so that's going to happen at x equals 0 and 1. That's why we had this interval. Remember, it said a belongs to 0 and 1 on the interval. Okay, since x equals a, this is in the interval from x is bounded between 0 and 1 included. Okay, where x is equals a here. So this problem, the largest error, right? So the largest error, right? So right here, the largest. Okay, so the largest, just give me a sec. Largest, let's see. For some reason my pen is acting up today. Yeah, the largest error. Okay, so the largest error happens, I'll say, yeah, that's a better error happens This error happens at one of the two. Yeah, I'll say one at the two endpoints. And one of the two endpoints. Okay, so we're going to say at x equals 0, right? So I'm going to put here at x 0, and we'll say at x equals 1. Well, not and, it's just saying or, because it says at one of the two endpoints, so it can't be and, it has to be or, right? Semantically, right? It has to be or. X equals 0 or x equals 1. Okay? All right, so we've clarified that, I think. Right, so let's move on to step 2. Now, step 2 now, right? Step 2, we want to actually model the problem. So now we're going to model the problem. We're going to try to take the minimization as the worst case error. Okay, worst case error. So all that means, right, is we're going to try and find the biggest, let me think. We're going to try and find the biggest endpoint. We're going to find the biggest endpoint error as possible. Sorry, we're going to find the biggest endpoint error as small as possible, right? Because the question was asking, find the A value that minimizes the error function. So the implication of what has been asked, right, for this, okay, is pretty much that, right? We're trying to, it means that we're trying to make the biggest endpoint error as small as possible, right? Because it's biggest, because it's a maximum, the error function is defined as a maximum here, right? So maximum, biggest, right? So look at the words carefully. Try to find the biggest endpoint error as small as possible, because the question says find this the value of A that minimizes the maximal error function. Okay, I hope that makes sense. So I don't know if you've noticed, but the harder math problems, the way to solve them only is to make sure you're understanding um, the language and the semantics of the problem being posed to you. And it's not always that easy. Okay, so you have to be able to think in a very logical framework. Okay, so that's very important. Okay, so let's do that. So here's the key idea: if the error, right, if the error at the left endpoint, okay, so error at the left endpoint. So if the error at that left endpoint is much bigger than the error at error, let me think. Is that left endpoint? No. If the error at the right endpoint is much bigger than the error at the left endpoint, the tangent line is too far. Okay, right? Is going to be too far to the other side. So the best tangent line should be, the best tangent line should balance the two endpoint errors. That's going to be our strategy. Okay? So when I mean endpoint errors, well, A belongs to the interval 0, 1, right? So since our right endpoint is much bigger, this guy 1 is much bigger than 0, okay? Then the tangent line is going to be too far to the other side, okay? So what we're going to do is we're not going to just use some random algebra. We're going to use a system for doing this. We're not going to guess. We're not going to use random algebra. We're not going to try every tangent line, right? To get the perfect tangent line here, as you can see. Okay. We're going to balance the error at 0 and the error at 1, as I mentioned. Okay. We're going to balance the error at 0 and 1. That's why it said A belongs to 0 and 1. Okay. Step 3 now. Okay. So let's look at step 3. Right. So step 3. Step 3 is we're going to execute. And when I mean execute our strategy of attack. Okay. So let's do that. So first off, we know that error, right? So the error, so I'm going to put down here the error, there at x equals 0, right? So at x equals 0, well, we know what that is, right? Let's look at the error function. We know that the error function was defined as capital E as a function of a is equal to the maximum, where 0 is smaller or equal to x, smaller or equal to 1, okay, of e to the x minus capital L subscript a of x, okay? We want to evaluate this error at x equals 0, okay? So that's what we're going to be looking at, right? We're going to look at the error at x equals 0. Now, I'm going to do this fast, and you can verify in your spare time, if you're interested, what it is. The error, right? Error at 0 is going to be equivalent to this, this expression, 1 minus e to the whole power of a plus a times e to the a, okay? That's the error at x equals 0, okay? Right, so if you don't understand how I got that, I substitute into this guy here, x equals a. If a is 0, x is 0, so e to the 0 minus L subscript of 0 of 0. We need to know what L of 0, the tangent line, is. We have an expression for the tangent line here, okay? Tangent line over here. Okay, tangent line there. Substitute x equals 0 everywhere, and you will simplify, add them together into the error function. Okay, so that's what we have right now. Now the error at x equals 1. Okay, so the error, then we also have the error. The other case is we have to look at the error at x equals 1 is going to be e to the, let's see here, so let's rewrite it again. So we know our error function is defined as a function of a is equal to the maximum where 0 is smaller or equal to x, smaller or equal to 1, of e to the x minus L subscript a of x, okay? At x equals 1, what we should come out with, right, is our error at 1. Error 1 is going to be e minus e to the a times 2 minus a, okay? All right, so we got both our error function equations at x equals 0 and x equals 1. All right, so I hope that is making sense. Okay, so let's go to the next page. All right, so we've got those guys. So the best tangent line is going to happen when these two guys are equal. Right, so again, the best tangent line is going to happen when these two errors are equal. Why do the two errors have to be equal? Because the tangent line is intersecting the curve. And since that curve, right, since we talked about the error in the curve, right, then the errors, the two error expressions that we have in terms of in terms of e, right, have to be equal because the curve is intersecting the tangent line, right? Okay, so let's do that. All right, so we've got so we're going to set them equal. So set, I'm going to say here, set. I'm going to set e of 0 equal to e of 1. Okay, so set e of 0 equals e of 1. Then that means that we're going to get e of 0, we know was 1 minus e to the a plus a e to the a, okay? And that's going to be equal to e of 1. Now, e of 1, okay? E of 1 is going to be equivalent to e minus e to the a by 2 minus a, okay? Right, I'm just taking the left endpoint error equal to the right endpoint error. And what this will simplify to, if we rearrange, click-like terms rearranged, we should be left with e to the a, right? E to the a is equal to e minus 1, okay? Right, but we want to find a. How do we find a? How do we find a? Well, we have to take ln of both sides, right? Simple. Right? Because y equals e to the x, that means x equals ln of y. So that means in this case, we are going to be left with, right? We're going to be left with the following. We're going to say that a is equal to ln on parentheses e minus 1. And that is our answer, okay? As you can see here, the result that we just found, okay, matches exactly the geometric description that I have here, okay? A equals ln of e minus 1. That is the value of a, that will minimize the error function, the maximal error function. Okay, so the tangent line, right? So in that case, the tangent line should touch x, e to the x, sorry, right? So that means, right? Right, so that means that that the tangent line, right? The tangent line should touch e to the x, should touch e to the x at, right? X equals, because x equals a, right? So at x equals ln of e minus 1. Okay, that is it, right? Well, we have step 4. We can verify this, right? Even though we have our answer, we need to verify, right? Right? Good mathematicians always verify what they're doing. So now we verify. So step 4, verify. So step 4, the verification phase, okay? Going to eliminate any ambiguity or nonsense. That's what verification is, okay? So this answer is between 0 and 1 as follows, right? It is between 0 and 1, right? So if we choose a equals 0, right? So think about it, right? So if yeah, if we choose a equals 0, a equals 0, the tangent line, right? So the tangent line is very very accurate, right? Very accurate, near 0, but worse than 1, worse than 1. Okay, as you can see in the description, this is the case, right? If we choose a equals to 0, right? The tangent line is going to be very near 0, right? Like this tangent line, the red line here, right? It may be not as inclined, it may be sloping down a bit more, right? Because it's near 0, but it's going to be worse than 1, but worse near 1 actually, okay? Now, if we choose, right? So let's just do this. If we choose, right? So if we choose a equals 1, the tangent line is very accurate near 1. tangent line is very accurate. Near near 1. Because again, at a equals 1, let's say a is 1, a here was between 1 and 2, okay? But if a is 1, it's getting very, very accurate, right? It's approaching the appropriate a that we need, okay? So the best tangent line is to touch somewhere in the middle, okay? Shouldn't be exactly at 1/2 because EDX will grow from the right side, okay? So that point is shifting slightly, okay? Try and see how it's shifting, okay? And for that reason, right, that's why we're getting that A equals ln, right? A equals ln of e minus 1, right? Okay. It's the perfect, think of it as a equilibrium point that we found, okay? Right? It makes the perfect, right? So A equaling ln of e minus 1 is making the perfect balance point. As I said, it's creating an equilibrium for the function e to the x and the tangent line. Makes the left error point, right error point, error equal. So this is going to minimize the worst case error. So I bet you haven't seen a tangent line question of this level of difficulty, even though in your calculus classes they were babysitting you with nonsense. Okay, my problems are no nonsense. They're the real deal, real mathematics. Okay, so the important lesson is not just the answer. The important lesson is the method. Okay, so the problem looks unfamiliar because it is not asking find the tangent line. That's what you guys are so used to. You don't even have to think about your questions anymore because the school system, university, or whatever system that you're in, the education system has given you nonsense for homework. Okay, the important lesson is the method. That's what I want to get down to. Right. Problem looks unfamiliar, as I said, for obvious reasons. It's not asking find tangent line. It's asking find a tangent line that performs best under the worst possible error. That is, that's something called a minimax problem. So if you are interested on the how interesting this is, look up minimax. Okay, you may want to look up minimax. Look up. So look up if you're interested on side work. You want to investigate more. Look up minimax. Minimax. Okay, minimax problems. Well, pull up some interesting stuff actually. Okay, it is interesting, right? So strategy is do not start the whole process by calculating, trying to deduce how they got the tangent line and work backward. Start by classifying what's important, right? This was not a routine tangent line problem. This was a convexity optimization problem. Okay. Now you're probably asking, um, I shouldn't be responsible for this. I haven't learned this. No, you haven't. But everything that I said here is algebraically within your grasp. And in university, so let's see, in the first year calculus class or whatever, um, they can give you any question they want as long as they taught you the algebraic methods. You don't have to be you have to be responsible for seeing that specific problem before and memorizing it. No, as long as you have the algebraic tools, you should be able to logically deduce how to solve a problem even if you haven't seen it before. Okay, so last thing I want to mention, okay, is so this is the full system. Full system was visualize, right? Again, my method for attacking hard problems, right? Visualize, right? With where e to the x is convex, right? So the tangent line lies below the curve. Then you want to model. So remember, visualize, underlining. Then you want to model. What's your model in this case? The first error happens at the endpoints. Then you want to execute, balance the two endpoint errors. Then you're going to verify. And the verification is the answer has to lie in between the interval 0, 1 as the equilibrium approximation. Okay? And therefore you get that A equals ln of E minus 1. Okay? This is the value that gives the tangent line e to the x with the smallest worst case error at 0 and 1. Okay. All right. So I hope you enjoyed today's video. So if you understand calculus in class, but you're freezing on hard midterms and final exam questions, okay, then this channel's for you. Right? Again, I'm Jason from STEM Online, right? And I help serious students solve hard calculus and physics problems using my systems technique that I mentioned: visualize, model, execute, and verify, right? The goal is not to get the answer. The goal is to know when the problem is going to look unfamiliar, okay? So I hope you enjoyed today's video. I do want to mention a few things. If you are still struggling on problems like these, I recommend you download my free PDF on my systems technique on how to approach it on on you know common concepts in calculus, like tangent lines or whatever. It's going to help you a lot. So please download my free PDF. Okay, it's for free. You get it in the bottom of this YouTube video. I'll upload it later. And there will also be, if you're still struggling with that, you may not have a systems problem, because sometimes people struggle semantically and logically, okay, on how to solve a problem. That's why I have my systems technique, okay? If you are struggling logically with how to do the problems, okay, like how I'm connecting one and one, I suggest that you purchase my book, Axioms, okay? It's about in introductory logic, right? And how to begin that's where you used to be starting. If you're learning math for the first advanced math for the first time, you should be starting with that book, okay? Because it gives you all the prerequisite knowledge, all the techniques that you need to know mathematically if you're not understanding what I'm doing. Nomenclature, logical deductions, all of that. Do that, get that book before tackling calculus. Okay, it's a prerequisite for calculus or any other advanced math course. Okay, and if you want more help, um, like personalized one-on-one help, nothing replaces coaching. I'm an expert mathematics coach. I can help you develop systems. I can help you solve the problems. And I can also help you develop more confidence in solving hard problems. Because a lot of you guys have anxiety. Okay. And the best way to do it is to take a deep breath, right? And apply tech systems that will help you solve a hard problem, right? It's not going to be as hard as you think it is. Your anxiety is making it worse. But I offer coaching, and you can reach out to me. There'll be a link in the description below. Okay. And if you're an independent learner, right, this channel is also for independent learners um, who happens to enjoy advanced mathematics, but you're not just any independent learner, you're advanced at calculus. You may want to get my second book, Advanced Integration Techniques. It's going to test you on, it starts off, hard and then it gets harder and harder. So if you like challenges, you like opening challenges, that is the book to get. It'll be in the description below. Again, like and subscribe. I appreciate all of I appreciate you guys for subscribing. Everyone who's subscribed, thank you so much. Keep the channel going, keep the messages going, and there'll be more interesting problems coming on later this week. Possibly I'm gonna try doing two more this week. Okay, one on IVT, intermediate value theorem, uh, and one calculus is very interesting calculus problem. All right, like and subscribe, guys. Have a good day.